Matrix operations. In this part, we are going to talk about some basic operations related to matrix. Those are transpose, addition, multiplication, and inner product. Those operations will be used throughout the term. Addition. If you are given two matrices, A and B, they are both m by m matrices. Then there's some A plus B. It has the same shape m by n, which is formed by component-wise additions. So there are two informations you want to know. Two key points. One, A plus B makes sense only if A and B have the same shape. If two given matrices are different in terms of shape, then you cannot add them together. And component-wise, addition. So if you are given two m by m matrices, you can do component-wise addition and get A plus B. We will see an example in the next slide. Matrix transpose. Matrix transpose is an operation of one matrix. So if A is given as m by n matrix, then it transpose AT is another matrix with n by m shape, whose columns are formed from the corresponding rows of A. So let's look at A, this A 2 by 2 matrix. What is its transpose? Then we put the first row of A as first column in the transpose, and put second row of A into second column of A transpose. Now the next question is, what is A plus A transpose? So A from here, we copy this down, 2, 3, 1, negative 5, added by A transpose, 2, 1, 3, negative 5. These two matrices are 2 by 2. They have the same shape. So we can add them together. So the first component by first component, 2 plus 2, which is 4. And second component to second component, so 3 plus 1. And 1 plus 3. Negative 5, negative 5. Negative 5 plus negative 5, which is negative 10. Multiplication. Matrix multiplication is not component-wise multiplication, first of all. So it's a little bit more complicated than addition. So we start with most simplest form of multiplication, so-called vector-vector multiplication. So suppose U is row vector 1 times n, V is n times 1, which is column vector. So U, we can think of U1, U2, U3, Un. And V is V1, V2, V3, Vn. But their length, their size are the same. One is row vector, one is column vector. Now we can multiply them together by using component-wise multiplication and take the sum. So if you are given the same size of row vector, column vector, then this is sum of element-wise multiplication, which is a number. This is a number, or one by one matrix. Now we can also define inner product. Inner product is an operation of two column vectors. So suppose U and V are column vectors of length n, then we can do inner product U dot V. This is closed dot, or you can solid dot. U dot V means inner product, which is equal to U transpose V. Because U is column vector, V is column vector, so U transpose is row vector, and this is column vector. So row times column, then element-wise multiplication, and then take the sum. So we know what to do. So if we write this again, then we can think of U1, U2, U3, all the way UN, dot product, V1, V2, V3, Vn, and the answer is we do element-wise multiplication, but add them together. So eventually we get a number. The sum of n numbers is a number. There's one example. A and B are given. So A is 1, 1. A is 1, 1. So A is given by transpose of row vector, which means column vector, 1, 1. B is transpose of this row vector, which is column vector. All right. What is inner product? Inner product is element-wise, 1 times negative 1 plus 1 times 1. So 1 times negative 1 plus 1 times 1, we get 0. So the inner product is 0. Now what is the angle between two vectors, A and B? So for two-dimensional vector, we can always put it into a plane. So 1, 1 is 1, 1. So A is here. Negative 1, 1. B is here. B is this point. Then what is the angle? Obviously, this is 90 degrees. So A is perpendicular to B, or you can say this is 90 degrees, or you can say pi over 2. All right, now we look at next two questions, very similar, but the only difference is P and Q, two vectors, are three-dimensional vectors, and we want to know inner product, and then their angle. So for the inner product, we write P dot Q, and P is given as transpose of row vector, which is column vector. And Q is column vector again with the same length, so we can do inner product. Now the inner product, the answer is supposed to be a number, but this is sum of three numbers. 1 times negative 1 plus 2 times 1 plus 1 times negative 1. And then this gives 0 as its inner product. Now number 4, what is the angle formed by vectors P and Q? P and Q are living in three-dimensional space, so it's not easily identified as a pictures in 2D plane. So this is living in three-dimensional space. So if we draw P and Q on computer screen, which is physically two-dimensional plane, then the angle is not clear. But one fact actually tells what the angle is formed by P and Q. The fact is that if the inner product of two vectors is 0, then they are orthogonal to each other or perpendicular to each other. So from this proposition, we can say P is perpendicular to Q because their inner product is 0. Now we can define matrix multiplication for the general cases. Not every two matrices are multiplicable to each other. They has to have the same, not the same shape, but specific shape. They have some specific conditions to be satisfied. So suppose A is n by n matrix, and B is n by p matrices. Then A and B can be A multiplied by B can be defined as M by P matrix with I, jth, nth is AI, Bj. Here AI is ith row, Bj is jth column of P. Now if A is a square matrix, then we can define A square as we can define A square as A times A, and A cubed as A squared times A. And all the way that AK equals AK minus 1 times A. I'm sorry that A is missing here. All right, the definition itself, just by looking at this, it's not that clear. We have to have some exercise to get familiar with this operation. But one thing I want to emphasize is, given two matrices, when you are asked to do multiplication, first thing is to identify if they are multiplicable or not. How do you do that? First, look at the shape of A, m by n. So you write the two numbers, row number and column number. And here, row number and column number. So you have to agree, you have to have the same. So the column number of A must be equal to the row number of B. So these two must be the same. Otherwise, we cannot do the multiplication. So remark. AB is well defined only if column number of A equals row number of B. All right, so there's one, we look at this example. Through this example, we also want to define very important matrix. It's called identity matrix. An identity matrix I, this is symbol, is a square matrix, first of all, with 1 in diagonal and 0 for others. So for example, what is 2 by 2 identity matrix? By this definition, this is definition indeed, identity matrix. So 2 by 2 identity matrix is a matrix of 2 by 2, which have 1 in diagonal and 0 for others. What is 3 by 3 identity matrix? What is 3 by 3 identity matrix? Then we can say it's a squared matrix of 3 by 3 and with diagonal entries 1 and otherwise all zeros. Now we are given another matrix B, which is 4, 3, 6, 1, negative 2, 3. Now we are looking at multiplication of IB. So I is 2 by 2 matrix. B is 2 by 3 matrix. We want to multiply them together. Before we multiply, we want to justify this multiplication makes sense or not, or well defined or not. So we look at second component of the I's shape and first component of B's shape. If they are the same number, then you can multiply together. So 2 equals 2. So in other words, this is a legal operation. This is well-defined operation. Now we do the rest computation by writing down I and B is 4, 3, 6, 1, negative 2, 3. Now, from the definition given here, it's not really clear, but when we look at this, so for example, we have 2 by 2 and 2 by 3, then the matrix you want to get obtained from this product has the shape of this 2 by 3. So the shape is 2 by 3. So indeed, you want to identify 6 numbers for this product. All right, now we do one by one. So from the definition, what you can observe is for this matrix A, we write each rows as A1, A2, AM. So in other words, you are screening A row by row, and B is column by column. So B1 is column vector, B2 is column vector, A1 is row vector, A2 is row vector. So it's better to screen row by row in first matrix and column by column in the second matrix. And for the first component, what you do is first row, first column, do multiplication. So for row vector multiplied by column vector, you do component wise. So 1, 0 times 4, 1, component wise multiplication. 1 times 4 plus 0 times 1, which is 4. This goes to the first spot. Now for the second spot here, what you do is, this is first row. This is in the in the product. First row, second column. So first row, second column. In other words, first row, second column. Okay. So first row, second column. So 1 times 3 plus 0 times -2, which is 3. We can keep going. We will find this is 6. I'm going to make a shortcut. You can do the practice by yourself. 1, -2. I will do computation for the last one. So this is located, its position is second row, third column. In other words, you want to do product of second row, third column. So if you do that, second row and third column, 6, 3, we get 0 times 6, 0 times 6 is 6. 1 times 3 will be 3. So it's 9. Oh, 0 times 6 is 0. I'm sorry. So at the end we get 3. This is 3. One observation: identity matrix to any matrix is B if it's well defined. So identity matrix is very special. It's something like 1 in the number system. So 1 times any number is, so 1 times any number A is going to be the same number A. So for the matrix, identity matrix plays the role of 1. Now find BI for 3 by 3 identity matrix. So B is 4, 3, 6, 1, -2, 3. And for 3 by 3 matrix, this is 1, 1, 1, 0, 0, 0, 0. And then we want to do BI. First, we look at the shape. B is 2 by 3. I is 3 by 3. Now, Is it multiplicable? Yes, the answer is yes, because if we look at 2 by 3 second component and 3 by 3 first component, they are both 3. They're equal to each other, so this makes sense. And the answer is a matrix, the product is a matrix of 2 by 3. And you want to determine 6 component. And if we operate, to save time, I'm not going to do this multiplication, but if you complete the calculation, you will have 4, 3, 6, 1, negative 2, 3. In other words, BI is the same as B. So I could preserve its product, and no matter it multiplied by from the left or right. Now we can compute, let's compute AB. Here, 2 by 2, and B is 2 by 3. A plus B. There are four operations we should do. So A plus B. First, A is 2 by 2, B is 2 by 3. They have different shape, so undefined. So we're done for the first question. What is AB? Multiplication, then 2 by 2 and 2 by 3. Because second component of the shape of A and first component of the shape of B, they agree each other. So that means you're supposed to get a matrix of 2 by 3. 2 by 3. So you need to determine 6 numbers. We're going to do this in the next slide, but let's first BA. B is 2 by 3, A is 2 by 2. Second component of B shape and first component of A shape. 3 is not equal to 2, so this is undefined, so we don't need to do calculation. And what about BT80? BT80, B transpose means you want to put row into column, so 2 by 3 becomes 3 by 2. AT is 2 by 2 matrix, so it transpose is another 2 by 2. So we get to B, the second component of B transpose, first component A transpose, they're both 2. So we can do the multiplication, and the multiplication gives a matrix of 3 by 2. 3 by 2. So you need to determine 6 numbers, but 2 columns, 3 rows. Here, 3 columns, but 2 rows. All right, to perform this, so there were 4 questions originally. Now we screened out, we eliminated 2 undefined operations, so they're just we don't need to do any more work. But for AB, so for next slide, I'm going to compute AB. AB. A is 2, 3, 1, negative 5, 4, 3, 6, 1, negative 2, 3. So we get 2 by 3. And for this, this position is first row, first column. Then here, first row, first column. In other words, 2, 3, and 4, 1. 2, 3, 4, 1. So 2 by 4, 3 by 1, 11. So we get this 11. Now I'm going to jump into this question. So this is in the second row, second column. In other words, in the matrix A and B, we want to do second row and second column. And the second column. So 1, negative 5, and 3, negative 2, which is, this is 3. Negative 5 times negative 2 is positive 10. So the result is 13. I'm going to leave the rest of them as exercise. Now what about B transpose A transpose? Of course we can do this step by step for calculations, but this takes a long time. But I'm going to show this property. AB transpose equals B transpose A transpose. So here are a couple of operation laws, and most of them are obvious, but this is a little bit special because we didn't have transpose, the concept of transpose in the number algebra. This is new for matrix algebra. So to do BTAT, instead of do the step-by-step calculation, what you can do is we rewrite this by matrix laws, A, B, transpose, T, and transpose. And suppose you get this answer, then you just transpose it. So it's supposed to be 11 and something, something, and something, 13, something. Another point I want to emphasize here is AB is not equal to BA. So in number algebra, A times B is always equals B times A, cumulative, but for matrix, AB is not BA in general. All right, we stop here.